We will return to our example of the distance traveled by a runner, but here we will interpret it graphically. Recall that we were understanding an example where the velocities of a runner were given by the following table. At t equals 0, they were traveling at 0 feet per second. At t equals 2, they were traveling at 8 feet per second. After 4 seconds, they were traveling at 14 feet per second. And after 6 seconds, they were traveling at 18 feet per second. And we wanted to estimate how far the runner traveled from t equals 0 to t equals 6. That is, how far they traveled in the first 6 seconds. To answer this, we found two estimates, our overestimate and our underestimate. To get our overestimate, we used that the runner was traveling at 8 feet per second in the first 2 seconds for a total of 16 feet, plus 14 feet per second for the next 2 seconds for a total of 28 feet, plus 18 feet per second for the last 2 seconds for a total of 36 feet. So we found out that the runner traveled at most 80 feet in the first 6 seconds. On the other hand, for our underestimate, we estimated that the runner traveled 0 feet in the first 2 seconds, 16 feet in the next 2 seconds, and 28 feet in the last 2 seconds for a total of 44 feet. Let's now break down these calculations and look at them graphically. Starting with our overestimate on the first time interval, let's visualize what the 8 times 2 means. Remember, this came from the fact that distance traveled is the velocity times time. In this case, to estimate our velocity, we use the velocity after 2 seconds, v of 2, times the time interval, delta t, which was 8 times 2 for a total of 16 feet. We can represent this with a rectangle of height 8 and width 2, and the distance traveled is the area of this rectangle, which is 16. How can we interpret this graphically? Let's start by looking at the graph of velocity. Suppose that t is represented on the horizontal axis and our velocity on the vertical axis. So the height of the curve gives us our velocity. How does this rectangle fit into our graph? Well, we are talking about the time interval from 0 to 2. So we want to put our rectangle so that delta t, the 2-second time interval, follows along the horizontal axis from 0 to 2. Notice that since our height is given by v of 2, which is 8, we pass through the point 2, 8 in the upper right-hand corner. Let's now use this way of thinking on our other time intervals. For the time interval from 2 to 4 seconds, we estimated that the distance traveled was the velocity at 4 seconds, 14, times the 2-second time interval, for a total of 28 feet. So we can represent this with a rectangle, now with height 14, and again with width 2. So its area is 28. We will now put this on the graph over the time interval from 2 to 4. Again, notice that we pass through the graph in the top right corner. That's because this point is 4, 14. Or in other words, the point 4, v of 4. Moving on to our last time interval, from 4 to 6 seconds, we calculated that the distance traveled was the velocity v of 6, which is 18, times the length of time, 2 seconds, for a total of 36 feet. Again, we can represent this with a rectangle, this time of height 18 and width 2, for an area of 36. Now, since this is talking about the time interval from 4 to 6 seconds, we will put it on our graph over the time interval from 4 to 6 seconds. Like the last two rectangles, since the height is given by v of 6, we pass through the point 6, v of 6 in the top right-hand corner. Now that we have visualized each term in our equation, 8 times 2, 14 times 2, and 18 times 2, we can visualize the distance traveled, which was roughly 80 feet, as the area of all the rectangles combined. That is, the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle. Let's now do this calculation for our underestimate, starting with the time interval from 0 to 2. To visualize this, we'll start with the fact that we approximated our distance as v at 0, which is 0, over the time interval of 2 seconds. So delta t equals 2. This can be represented with a rectangle of height 0 and width 2, which gives an area of 2 times 0, which is 0. We can represent this on the graph over the time interval from t equals 0 to t equals 2. Notice here that the height of our graph was given by v of 0, which was 0. So we pass through the point 0, 0, which is the left-hand side of our rectangle. Moving on to the other intervals, we will next look from t equals 2 to t equals 4. Here, the distance traveled was approximated as the velocity at 2 seconds, which was 8, times the time interval, which was 2 seconds, for a total of 16 feet. We can visualize this as a rectangle with height 8 and width 2, giving an area of 16. Since here we are looking at the time interval from 2 to 4, we'll put this on our graph over the time interval from 2 to 4. Notice here that since the height of our rectangle was given by v of 2, our rectangle touches the graph at the point 2, v of 2 in the top left-hand corner. In our last time interval, from t equals 4 to t equals 6, we calculated the distance traveled using the velocity v of 4, which was 14, and delta t equals 2, for a total distance of 28 feet. This can be represented as a rectangle with height 14 and width 2, giving an area of 28. Similarly, since we are talking about the time interval from 4 to 6, we will put this on our graph over the time interval from 4 to 6. Notice that since the height of this rectangle was found as v of 4, it passes through the left-hand point 4, v of 4. So now that we have visualized the distance traveled over each time interval, we can visualize the total distance traveled over the 6 seconds as the area of all the rectangles combined. That is, the area of the first rectangle, which is 0, plus the area of the second rectangle, which is 16, plus the area of the third rectangle, which is 28, for a total of 44. We will now do graphically for this example what we did algebraically. That is, we will get a better understanding of what happened if we take smaller time intervals. So we will look at our table of t versus v, where we know the velocities at every second instead of every 2 seconds, and ask the question, how far did the runner travel from t equals 0 to t equals 6? Remember that for our overestimate, we approximated that the runner traveled at most 72 feet, and for our underestimate, we approximated that our runner traveled at least 54 feet. Let's now interpret this graphically, starting with the first time interval from 0 to 1 in our overestimate. Let's now visualize our calculation that the distance traveled was 4.5 times 1 as a rectangle with height 4.5 and width 1, giving an area of 4.5. As we did before, we'll see how this fits into our graph of v of t. Since we are looking at the time interval from 0 to 1, we'll put the rectangle over the time interval from 0 to 1. Notice again that since our height is given by a v of 1, we pass through the point 1 v of 1 in the top right hand corner. Moving on, we look at the next time interval from 1 to 2. Here, we calculated that the distance traveled was v of 2, or 8, times the change in time of 1 second, for a total of 8 feet. We can represent this as a rectangle with height 8 and width 1, for an area of 8. Here we are talking about the time interval from 1 to 2, so we'll place it on our graph from 1 to 2. Repeating this process, we get that we can visualize the distance traveled over the time interval from 2 to 3, which is given by the calculation v of 3 times delta t, or 11 times 1, with a rectangle of height 11 and width 1, for an area of 11. This gives a rectangle of area 11, which can be added to our graph over the time interval from 2 to 3. Next, we look at the time interval from 3 to 4. Here we computed that the distance traveled was v of 4 times delta t, which was 14 feet per second times the 1 second time interval to give 14. This can be represented as a rectangle of height 14 and width 1. In this rectangle of area 14 can be put on our graph over the time interval from 3 to 4. The distance traveled over the time interval from 4 to 5 was calculated as v of 5, 16.5, times delta t, which is 1 second. This can be represented as the rectangle of height 16.5 and width 1. This rectangle of area 16.5 can be added to our graph over the time interval from 4 to 5. Lastly, over the time interval from 5 to 6, we computed the distance traveled as v of 6, which is 18, times delta t, which is 1. This calculation can be represented as a rectangle of height 18 and width 1, giving an area of 18, and can be put on our graph over the time interval from 5 to 6. Now, just as we did in understanding our overestimate with 2-second time intervals, we can interpret the total distance traveled, which is 72 feet, as the area of all the rectangles combined. This is because the area of each rectangle represents how far the runner traveled over each time interval. Let's now repeat this process for our underestimate. Over the first time interval, from 0 to 1, the distance traveled was approximated as the velocity at 0, which is 0, over the 1 second time interval. So we approximated the distance traveled as 0 feet. This can be represented as a rectangle with height 0 and width 1, giving an area of 0 feet. We will put this on our graph over the time interval from 0 to 1. Moving on to the next time interval, we approximated that the distance traveled was v at 1, 4.5, times 1 second, for a distance of 4.5 feet. This can be represented as a rectangle of height 4.5 and width 1, giving an area of 4.5 representing the distance. We will add this to our graph over the time interval from 1 to 2. Notice here that since the height of this rectangle is v of 1, we pass through the point on the graph 1 v of 1. Next, in the time interval from 2 to 3 seconds, we approximated the distance traveled by using the velocity v at 2, which was 8, times the time interval, which is 1 second, for a distance of 8 feet. This multiplication can be visualized as a rectangle of height 8 and width 1, giving an area of 8, which represents the distance traveled. This rectangle we will put on the graph over the time interval from 2 to 3. Carrying on, we look at the time interval from 3 to 4. Here we calculated the distance as v of 3 times delta t to be 11. This can be represented as a rectangle of height 11 and width 1, giving an area of 11, which can be put on our graph over the time interval from 3 to 4. Then, on the time interval from 4 to 5, we calculated that the distance traveled was v of 4 times delta t, which is 14 times 1, or 14 feet. This can be represented as a rectangle of height 14 and width 1, giving an area of 14, representing the distance traveled. This can be placed on our graph over the time interval from 4 to 5. We finally look at the last time interval from 5 to 6. Here we calculated that the distance traveled was approximately v of 5 times delta t, or 16.5 times 1, giving a rectangle of height 16.5, width 1, and area of 16.5, which can be put on our graph over the time interval from 5 to 6. Now, since the area of each rectangle represents the distance traveled over that time interval, the total distance traveled can be visualized as the area of all the rectangles combined. Let's now use this visual understanding to better approximate the distance traveled. We just visualized our overestimate of 72 feet and our underestimate of 54 feet. Now, how do we make our estimates even better? That is, how do we get a smaller range of how far the runner could have traveled? We answered this question before by saying we needed to take smaller time intervals. So let's look graphically at adding more time intervals, which will make each time interval smaller. In our first approximation, we used 3 time intervals, which were 2 seconds each. We will refer to the number of time intervals as n and the length of the time interval as delta t. Here we calculated an underestimate of 44 feet and an overestimate of 80 feet, and represented these using the rectangles below. So we could conclude that the distance traveled was somewhere between 44 and 80 feet. We then improved on this by changing the number of time intervals to 6, making them each 1 second. Here we found that our underestimate was 54 and our overestimate was 72. So we could conclude that the distance traveled was between 54 and 72 feet. Now, how can we make this even better? Let's increase the time intervals from 6 to 12, making them each half a second. Notice that as the number of time intervals, n, increases, the length of the time interval, delta t, decreases. We did not compute this algebraically, but if we had, we would have found that the underestimate was 58.58 feet and represented by the area of all the orange rectangles, and the overestimate would be 67.63 feet and could be represented as the area of all the green rectangles. So this tells us that the distance traveled was somewhere between 58.58 feet and 67.63 feet, since we know the actual distance traveled is higher than our underestimate but lower than our overestimate. We can now make our estimate even better by bumping our number of intervals up to 24, making them each only 1/4 of a second long. Again, we did not calculate the over and under estimates algebraically, but we can see them here graphically. And if we had calculated them algebraically, we would have gotten that the underestimate was 60.88 feet and the overestimate was 65.4 feet, which means that the distance traveled must be somewhere between 60.88 feet and 65.4 feet. To make this even better, we increase the number of intervals again, this time to 48, making the length of each interval only 1/8 of a second. Again, we did not calculate the over and under estimates, but we can visualize them. The underestimate can be visualized as the area of all the orange rectangles, while the overestimate can be visualized as the area of all the green rectangles. If we were to calculate this algebraically, we would get that the underestimate is 62.01 and the overestimate is 64.28. So the distance traveled is somewhere between 62.01 feet and 64.28 feet. Notice that as n increases, that is delta t decreases, the over and underestimates get closer together. That is, we have a smaller range for the actual distance traveled. If we increase this even more to n equals 96, giving a time interval of 1/16 of a second, we could calculate that the underestimate is 62.58 feet and the overestimate is 63.71 feet. So we know that the distance traveled is somewhere between 62.58 and 63.71. So what's happening graphically as we take more and more intervals? Notice that in our graph for the underestimate, the area under all the orange rectangles is getting closer and closer to being the area underneath our curve. And our overestimate is also getting closer and closer to being the area under our curve. And if we take n off to infinity, meaning that delta t is going to 0, we get that the underestimate equals the area under the curve, and the overestimate also equals the area under the curve. So we can conclude that as n goes to infinity, the overestimate and the underestimate both give us the area under the curve. And since the actual distance traveled must be between these two things that are the same, the distance traveled must be the area under the curve. Let's summarize what we just found. If s of t is our position and v of t is our velocity, then we know that v of t is the derivative of s of t. What we just found was that the distance traveled from t equals 0 to t equals 6 is given by the area under the curve of v of t from t equals 0 to t equals 6. In general, the distance traveled from t equals a to t equals b can be found as the area under the graph of v of t from t equals a to t equals b for any time interval from a to b. In other words, our change in position from t equals a to t equals b is the area under the graph of v of t from t equals a to t equals b. Or putting position in terms of the function s of t, the change of s of t from t equals a to t equals b can be calculated as the area under the graph of v of t from t equals a to t equals b. So in other words, we can compute the distance traveled by calculating the area below the graph of v of t. Notice that this allows us to turn a long algebraic calculation into something graphical.